I went ahead and drew out both structures for both sides of the equation here, just to save a little bit of time, but we'll start from the beginning. So we need to identify our acid and our base on this left-hand side here. So the acid is going to be this guy here, the thing that donates protons. So you have this little group over here with the nitrogen that has 2 protons that can donate. And the base is going to be that which accepts protons, which is this guy over here. So next step is drawing the curved arrow, going from this right here, showing this set of electrons attacking one of these protons. We'll just have it attack that one on top. And then of course having that one go ahead and attack the next, or excuse me, the nitrogen. So we'll go ahead and draw that now. And then that guy's gonna come down here. Boom. So that's going to create that set over there on that side. So now we have to label the conjugate acid and the conjugate base. So we have this guy as the acid and this guy as the base. Okay. And then on the right hand side, the conjugate base is going to be that which is created from the acid. So after it donates its protons, so we'll just call this the C base, and then by default the C acid. So now we have our base, our acid, and our conjugate acid and our conjugate base ready to go. So now we have to identify the strong acid, strong base, and weak base. So we'll go ahead and do it through Ario. So starting from the beginning, first letter is A for atom, and we notice that so essentially the strong acid it creates the most stable conjugate base. So the question here is, which base is stronger? Is it this conjugate base over here that was created from this acid, or is it this base that would have been created from that acid over there? So we're really looking at this molecule here and this molecule here. So just starting at A, atom, this has nitrogen, this one over here has sulfur, and going by row on the periodic table, the nitrogen is going to be more electronegative. Now, just to make sure that we've controlled for all other factors, let's go through the other letters. So R is resonance, which is going to be pretty much exactly the same. Not exactly the same, but in terms of structure, exactly the same. The molecules are almost the same except for the fluorine versus the chlorine and the sulfur versus the nitrogen. The same steps away from other electronegative molecules. So this nitrogen over here is the same number of jumps away from that fluorine as this sulfur is right here from that chlorine right there. So that's about the same. And even though the fluorine is also even more electronegative than the chlorine, so that kind of helps the case for this guy over here on the right. And then the orbitals in all these cases, in the case of this base and this conjugate base, are going to be sp3 orbitals in both cases. So essentially, starting with A and then going all the way down, we find that this conjugate base right here is actually going to be the weak base, which was created by the strong acid, the Sa right there, which would make this guy right here the strong base, and this guy right here the weak acid. So looking at this right now, which acid would we expect to have the higher pKa value? So weaker acids have higher kPa values. So this one would probably have the highest kPa. And this acid over here, because it's a stronger acid, would have a lower kPa. Because lower numbers and, of course, negative ones have end up being stronger acids than those higher. And each single-digit jump is an order of magnitude in terms of acidity. So last thing is predicting the equilibrium position. So essentially, it's going to favor the right-hand side, because equilibrium, when all of these other things are equal, will favor the side that has the more stable conjugate base. And the more stable conjugate base, of course, holds a negative charge better. So therefore, these two species on the right-hand side will be more present in the highest concentration at equilibrium.